Hello, and today our group will be presenting our project, which is designing and simulating an off-grid solar photovoltaic system. Our project is to design and simulate a complete solar PV system in a MATLAB Simulink. It's to provide a continuous 230 volt of AC power supply to a community in Langkawi Island. We focus on the model-based design and simulation of a complete off-grid solar PV system that's capable of supplying standard AC loads in home. This is our general solar PV system. Our system divided into three fundamental subsystems, which is solar PV array, DC-DC converter with maximum power point tracking, and DC-AC inverter. I will continue in the modeling of the solar PV panel. My part is divided into four, which is introduction to solar PV panel specification, calculation, also simulation and result. Firstly, I will start with the introduction to solar PV panel. The PV is a short form from the word photovoltaic, and the photovoltaic is a combination from two words, which is photo means light and voltaic means electricity. And from the name itself, we can describe it as a device that can convert sunlight into a DC electricity. Next, I will explain about the working principle of the solar PV panel. First, the photon from the sunlight will travel and strike the solar panel. They deliver the energy to the panel's key component, which is PV cell, that are made of a semiconductor material. When that happens, we create a special environment inside the cell by doping the silicon. This will cause forming of two layers, which is N-type layer and P-type layer. When these two layers meet, an internal electric field is created. This movement of electron creates a flow of direct current or DC electricity. This is the same type of electricity that you get from the battery. Next, for the PV array specification, we choose a model of JA Solar for maximum 500 watt rated power. The maximum power voltage for the solar panel is 38.58 voltage, and maximum power current for the solar panel is 13.04 ampere. Open circuit voltage is 45.59, and the short circuit current is 13.93 ampere. We also assume that the monthly average power usage for the home is 900 kilowatt, which is divided by 30 days is 30 kilowatt per day, and the average Malaysia peak hour is 4.5 hours per day based on data research, and the PV safety margin we put is 20%. I also put an assumption for the battery that has depth discharge of 90%, battery voltage for 48 voltage, and battery efficiency for 90%. For the calculation, firstly we need to calculate the energy required by the model. So, we assume that the power usage every day is 30 kilowatt per hour, and it will be divided by the inverter efficiency and battery efficiency, and we get the power by 35.09 kilowatt per hour per day. And from that, we can calculate the array sizing calculation by dividing it with Malaysia average peak sun hour, which is 4.5, and times it by the safety margin, and we get it, the final power is 9.36 kilowatt power. And to ensure the stability of the system, we took the final power is 10 kilowatt power. And finally, for the final array configuration and arrangement, we divided the final power with 500 watt rated power from the array, and we get the panel is 20 panel. And to ensure the reliability performance, we took the 21 panel and arranged it in the 3 series connected panel of the 7 parallel string. Final part of the calculation is the electrical parameter of configured array. From the configured value of the array, we times it by the series and the parallel value of the array arrangement of the model, and we get the maximum power voltage is 115.59 voltage, open circuit voltage is 136.62 voltage, maximum power current is 91.28 ampere, and short circuit current is 97.51 ampere. It to provide a sufficient power to meet a daily energy requirement and maintain operating voltage and current to ensure the reliability operation of the home appliances. For our simulation in MATLAB Simulink, we model the entire system, and when the PV arrays convert sunlight into the DC power, the power then will go directly into a DC-DC boost converter to condition it. From the simulation, we know that the power generated from the PV array is depends on its surrounding condition, which is irradiance and temperature. The result on the graph shows clearly the classic knee of the current voltage curve and the peak of power voltage curve. The key insight is the impact of the temperature. At 25 degrees Celsius, we achieve a peak power of nearly 10 kilowatt, but at the 45 degrees Celsius, the performance degrades. A maximum power drops to just 8 kilowatt. This confirms that the higher temperature significantly reduces a solar array's voltage and overall power output.
So hi, my name is Muhammad Ali Fisham, and for my part, I'm going to talk about DC to DC boost converter. I'm going to explain why what is DC to DC boost converter, why we have to use DC to DC boost converter, and what method that I use in MPPT, and the calculation for the boost converter, and lastly, the simulation and result. So, what is DC to DC boost converter? A DC to DC boost converter is an electrical circuit that step up the DC voltage. It consists of an IGBT switch, MOSFET switch, inductor, capacitor, and a diode. So, boost converter are commonly used in PV systems, battery systems, and electric vehicle. So, why do we need boost converter in our circuits? This is because the PV array supply a low voltage and is not enough for the load. So, we need an electrical circuit that can step up the voltage. So, by working together with the MPPT, the boost converter can improve the efficiency and the system performance by supplying a higher voltage to the inverter. So, what is MPPT? MPPT stands for maximum power point tracking. So, the method that I choose for MPPT is the pertube and observe method. It is a simple MPPT method technique that is used to extract the maximum power from a solar panel. So, how does this method work? So, the pertube and observe method is the idea is to slightly change the duty cycle or the pertube the duty cycles of the DC to DC converter and observe how the PV power responds to it. So for example, as you can see at my right side, the graph, if the power is decreasing, the PNO algorithm will continue increasing it, which means reduce the duty cycle until it reaches the maximum power. So if the power is decreasing, the PNO algorithm will reverse the direction and decrease the voltage, which is increase the duty cycle until it moves back to the MPP. So this process will repeat until the operating point reach the maximum power point. So this is the calculation part where we find all of the important parameters, and I've also checked if the converters are working in CCM mode or not. So this is the results for my simulation. As you can see, the percentage difference for my input voltage compared with theoretical and simulation is 3.87. The output voltage is 1.68. The input current is 2.97, and the output current is 1.13. And all of the overall percentage difference is below 5%, and I believe that my simulation has been achieved successfully because we reached our desired goal, which is to reach output voltage around 280 volt, and we got 273.6, and it is still in that range. So why all of this difference occurs is because in theoretical we assume all of the components is ideal, but in simulation it includes switching ripple, inductive behavior, and diode voltage drops. So this is the reason why we have a small difference between simulation and theoretical. So overall, the simulation closely matched the theoretical value, and it shows that the boost converter design works correctly.
In this slide, we analyze the effect of changing the switching frequency from 50 kHz down to 10 kHz while keeping all other parameters the same. From the voltage and current waveform, you will notice that the DC level for both the input and output remains unchanged. This is because the DC gain boost converter is determined by the duty cycle, not the switching frequency. What does change, however, is the ripple. At the lowest switching frequency of 10 kHz, the voltage ripple becomes noticeably larger and the waveform appears less smooth. This happens because lower switching frequency allow more inductor current variation per cycle. So the key takeaway here is that switching frequency mainly affect waveform quality and ripple size, but not the average output voltage. On this slide, we study how the boost converter responds when the solar irradiance is reduced from 1000 watt per meter squared to 500 watt per meter squared. Looking at the voltage graph, we can see that both V in and V out decrease. From the measurement window on the right, the input voltage dropped to about 73.52 volt, which is a 36% reduction compared to full irradiance. Similarly to the output voltage decreased to around 248.2 voltage, representing a 34.7% drop. This behavior is expected because the lower irradiance levels means the PV panel generates less power, so the converter receives a smaller input. Despite this reduction, the boost converter still operates correctly. The important condition, V out remains higher than V in is maintained. This confirms that even under reduced sunlight, the converter can still step up the voltage as designed. Hi, my name is Muhammad Khairul Ilham, and my task is to do the simulation for the DC-DC converter and overall circuit simulation. In the DC-DC converter, PV array are set using the calculation value to get the input voltage around 115.59 volt, and the current input is 1.3158 ampere. Inductor are set to 1.85 millihenry, output capacitor are set to 0.96 microfarad, and line capacitor are set to 0.69 microfarad. We add resistor value 288.79 ohm at the output so that the value for the simulation are close to the calculation value. Hi, my name is Muhammad Khairul Ilham, and my task is to do the simulation for the DC-DC converter and overall circuit simulation. In the DC-DC converter, PV array are set using the calculation value to get the input voltage around 115.59 volt.
Today, I will be explaining about the design, simulation, and the performance of the DC-AC inverter in our solar PV system. The inverter is a crucial part in converting the DC voltage from the solar panels into the usable AC voltage for the residential. In our design, the full bridge inverter was chosen because it can produce both the positive and negative halves of the AC waveform, which is important for the creating a stable and smooth output. Okay, next for the inverter design, we calculate that we want the voltage output is 230 volt. And the input voltage that we got from the inverter is the 380 volt. And then the output frequency is 50 Hz. The peak-to-peak current ripple we choose is 20%. And the switching frequency 20 kHz. And the voltage ripple is 5%. By these all parameters, we can calculate the duty cycle, which is we got the 0.855, and then we can calculate the current output, which is we got the 5.43 amperes, and also we got the capacitor value, which is the 23.6 microfarad, and also the inductor value, which is 2.54 millihenry. Next, we model the inverter in MATLAB Simulink to simulate its behavior under the real-world condition. As we know, the voltage input and the current input for the inverter is actually the same with the voltage output and the current output from the DC-DC converter. And the voltage output that we got from the calculation is 230 volt, and from the simulation, we got 238.6 volt, slightly higher from the calculation. And the current output for the calculation, we got the 5.43, and for the simulation, we got the 4.16 ampere, which is slightly lower than the calculation. Okay, next we will talk about the inverter behavior under the different conditions, which is like variation in the irradiance, load, and the switching frequency. At low irradiance, which is 200 watt per meter square, the output voltage drops significantly to 55.94 volt, and the output current reduced to 1.15 ampere. This is expected because lower irradiance means less solar energy is available, which leads to reduce the power generation. On the other hand, at high irradiance, which is 1000 watt per meter square, the output voltage increased to 238.64 volt, and the current to 4.16 ampere, demonstrating the inverter's ability to adapt the varying solar inputs and maintain a stable output. When the load was set to 10 ohms, the output voltage increased to 248.8 volt, and the current was 2.48 ampere, as expected, due to the lower resistance drawing more current. When the load was increased to 50 ohms, the output voltage slightly decreased to 241.7 volt, and the current dropped to 2.26 ampere, which aligns with the Ohm's law. As a higher load resistance reduces, current will be higher. At a switching frequency of 50 kHz, the output voltage is 245.6 volt, and the output current was 4.08 ampere, which is provide a good balance between the efficiency and the voltage regulation. However, when the switching frequency was increased to 100 kHz, the output voltage decreased slightly to 243.1 volt, and the current dropped to 3.66 amperes.
For overall circuit, I remove the voltage supply from the DC-AC inverter and connect it to the output voltage for DC-DC converter as the input voltage. All the parameters are set using the calculation value, especially for modulation index, and the result for the output voltage in AC is 238.64 volt. For overall circuit, I remove the voltage supply from the DC-AC inverter and connect it to the output voltage for DC-DC converter as the input voltage. All the parameters are set using the calculation value, especially for modulation index, and the result for the output voltage in AC is 238.64 volt. For overall circuit, I remove the voltage supply from the DC-AC inverter and connect it to the output voltage for DC-DC converter as the input voltage. All the parameters are set using the calculation value, especially for modulation index, and the result for the output voltage in AC is 238.64 volt. For overall circuit, I remove the voltage supply from the DC-AC inverter and connect it to the output voltage for DC-DC converter as the input voltage. All the parameters are set using the calculation value, especially for modulation index, and the result for the output voltage in AC is 238.64 volt. For overall circuit, I remove the voltage supply from the DC-AC inverter and connect it to the output